Today we're going to talk about concavity and points of inflection. So we'll start off with some definitions. A function f of x is said to be concave upward if the curve lies above its tangent lines. And a curve is said to be concave downwards if it lies below its tangent lines. Then we say c is a critical value of the second derivative if the second derivative is 0 at c or if the second derivative is undefined at c. That's a very similar definition to the critical value we talked about in 10.1, but here we're talking about the critical value of the second derivative. So we're looking for where the second derivative is 0 or where the second derivative is undefined. If c is a critical value of the second derivative and your function switches concavity at c, then the ordered pair c comma f of c is a point of inflection. So it doesn't matter if you go from concave upwards to concave downwards or concave downwards to concave upwards. If your function switches concavity at c, then c comma f of c is a point of inflection. Now we have a special point of inflection that is called the point of diminishing return if your function changes from concave upwards to concave downwards. So if your function goes from concave up to concave down, not only is that a point of inflection, but it is also a point of diminishing return. The point of diminishing return is the point where your sales stop increasing and they start to fall off. So that's what it means in the business sense. So here's a graph, and I drew a bunch of tangent lines. So if you notice this light green, this blue, this purpley dark blue, and this pink tangent line all lie above the curve. When the tangent lines are above the curve or the curve is below the tangent lines, we call that concave downwards. Here, this dark green, blue, red, and another blue tangent line here are all lying below the curve, which means the curve is lying above the tangent lines, which means it's concave upwards. So a little thing that we help remember is that concave down makes a frown, and then concave up makes a cup. That's the best way we can come up with something that rhymes. Unfortunately, concave up doesn't rhyme with smile. So we have a test for concavity. So you got to let c be a critical value of the second derivative where the second derivative is equal to 0. Then your function, your original function, will be concave upwards where your second derivative is positive, and your original function will be concave downwards where your second derivative is, that's a typo, that should say negative. This should say negative right here. Change that to a negative, please. So determine the concavity of f of x equals x to the fourth plus 2x cubed minus 36x squared plus 10x minus 1 and identify any points of inflection. Your first step is to find the critical values of the second derivative. The reason being is that at the critical values of the second derivative, that is the only place where your function can change from concave up to concave down. So we're going to find those critical values of the second derivative, which means we need to find the second derivative. In order to find the second derivative, we have to find the first. So I found the first derivative, 4x cubed plus 6x squared minus 72x plus 10. And then we can find the second derivative, 12x squared plus 12x minus 72. We'll set that second derivative equal to 0, factor out a 12, and this factors into 12 times x plus 3 times x minus 2. Setting that equal to 0, we'll set the x plus 3 equal to 0 to get negative 3, and we'll set the x minus 2 equal to 0 to get x equals positive 2. So we have two critical values of the second derivative, negative 3 and positive 2. Step 2, we'll draw a number line labeling all the critical values of the second derivative. So labeling them in order, negative infinity to negative 3 to 2 to infinity. We'll determine the intervals outside and in between the critical values. So starting at negative infinity, we'll stop at negative 3. From negative 3, we'll stop at 2. And from 2, we'll stop at infinity. Then we'll choose a test value from each interval to plug into the second derivative to determine concavity. So you can pick any x value in here, here, and here. So I picked negative 4, 0, and 5. The second derivative is either positive or negative on this entire interval, which means your function is either concave upwards or concave downwards on this entire interval, because the only place it can change is at the critical values negative 3 and 2. So when I plug in negative 4, I get 12 times negative 4 plus 3 times negative 4 minus 2. And the number it turns out to be is irrelevant. You don't even need to calculate it. You just need to know, is it positive or is it negative? Well, 12 will be positive. Negative 4 plus 3 is negative. Negative 4 minus 2 is negative. And a positive times a negative is a positive. So that means the second derivative is positive on this entire interval, which means your original function is increasing on this, is concave upwards on this entire interval. Plug in 0. I'll just plug that right into the derivative, second derivative. 12 times 0 squared plus 12 times 0 minus 72 gives me negative 72. The number itself doesn't matter, just the fact that it's negative. So that means that the second derivative is negative on this entire interval, which means your original function is concave downwards on this entire interval. And then we'll plug in 5 into the second derivative, and we get 12 times 5 plus 3 times 5 plus 2, which is a positive times a positive, which is times a positive, which is a positive. So that means the second derivative is positive on this entire interval, which means your original function is concave upwards on this entire interval. So ordinarily I would come back to this number line, but to show you in order, using that number line, I would label that first interval as concave upwards, that second interval is concave downwards, and that third interval is concave upwards. And so now we have enough information to answer the question. My function is concave upwards from negative infinity to negative 3 and 2 to infinity. It's concave downwards from negative 3 to 2. These are all intervals. Now our points of inflection are ordered pairs. So we have points of inflection. Where do we change concavity? We went from up to down at negative 3. So we have a point of inflection at 3, comma, the original function evaluated at 3, which when you plug negative 3 into the original function, you get negative 328. And we switched from concave downwards to concave upwards at 2. So the ordered pair 2, comma, the original function evaluated at 2, which is negative 93, is a point of inflection. So we have 2 points of inflection, negative 3, comma, negative 328, and 2, comma, negative 93. But notice at negative 3, we went from concave upwards to concave downwards. So not only is this a point of inflection, but it is also a point of diminishing return. Let's look at another example here. Determine the concavity of the function x to the 4th over 12 minus x cubed over 2 plus x squared plus 10x minus 9. Now this dividing by 12 is the same thing as multiplying by 1 over 12. It's just a coefficient, and coefficients just carry through. So you can basically just leave the 12 alone. So you can pull out the 1 over 12 if you want to, and then take it 1 over 12 times the derivative of x to the 4th. It'll turn out to be the same answer. So we'll take the derivative, the first derivative, which is going to be 4x cubed over 12, minus 3x squared over 2, plus 2x plus 10. This will reduce to x cubed over 3, minus 3x squared over 2, plus 2x plus 10. Now we can take our second derivative. And again, this 3 and this 2, these are just coefficients. They can just carry through. So that's going to give me 3x squared over 3 minus 6x over 2 plus 2, which will reduce to x squared minus 3x plus 2. So we'll set that equal to 0. X squared minus 3x plus 2 equals 0. And we'll factor. We get x minus 2 times x plus 1. And we get two critical values, 2 and 1. So step 2 in green here, I drew this number line. Step 3 in light blue, I found my intervals negative infinity to 1, 1 to 2, and 2 to infinity. Step 4 in this red color here, I chose an x value from each of these intervals. I chose 0, 1.5, and 5. And now I'm going to plug those into the second derivative to determine the sign of the second derivative. Plug in 0, I get 2, which is positive, so we're concave upwards on that entire interval. Plug in 1.5, I get 1.5 minus 2, which is a negative, 1.5 minus 1, which is a positive, and a negative times a positive is a negative, so we're concave downwards on that entire interval. And plug in 5 into the second derivative. 5 minus 2 is positive, 5 minus 1 is positive, a positive times a positive is a positive, so we're concave upwards on that entire interval. And so now I know that I am concave up from negative infinity to 1, concave down from 1 to 2, and concave up from 2 to infinity, I'm ready to answer the question. Now, did I switch concavity anywhere? I went from concave up to down at 1. So at 1, comma f evaluated at 1, I have a point of inflection. And I went from concave down to concave up at 2. So at 2, comma the original function evaluated at 2, I have another point of inflection. Are either of those a point of diminishing return? Well, notice here we went from concave up to concave down, so that's going to give us that point of diminishing return. So I have 2 points of inflection, 1, 19/12 and 2, 37/3. But notice this point of inflection, since it went from concave upwards to concave downwards, is also a point of diminishing return. Let's look at another example. We'll determine the concavity of x to the 4th over 12 minus x cubed over 3 minus 4x squared plus 7x minus 9, and identify any points of inflection again. So we'll take the derivative. This 12 is a constant. It can just stay. 4x cubed over 12 minus 3x squared over 3 minus 8x plus 7, and reduce to get x cubed over 3 minus x squared minus 8x plus 7 as your first derivative. This over 3 is just a coefficient. Leave it alone. So that second derivative will give me 3x squared over 3 minus 2x minus 8, which gives me x squared minus 2x minus 8. We'll set that equal to 0 and factor. Set the factors equal to 0, and I get critical values of 4 and -2. So in this light green here, I labeled my number line -2 to 4. I found my intervals to be -infinity up to -2, -2 to 4, and 4 to infinity. And I chose random x values in each of those intervals to plug into the second derivative to determine if the second derivative is positive, so therefore your function's concave upwards, or if your second derivative is negative and therefore your function is concave downwards. When I plugged in -3, I'll just plug it into this factored form here. -3 minus 4 is negative. -3 plus 2 is negative. A negative times a negative is a positive, so we're concave upwards on that entire interval. Plug in 0 into the original non-factored form of the second derivative, and I get 0 squared minus 2 times 0 minus 8, which gives me -8, which is negative. So we're concave downwards on this entire interval. And then plug in 5. We have 5 minus 4 times 5 plus 2 gives me a positive times a positive, which is positive, so we're concave upwards on this entire interval. So we're concave up from -infinity to -2, and from 4 to infinity. From -2 to 4, we're concave down. We did switch concavity here, so we have a point of inflection. We did switch concavity here, so we have another point of inflection. And at this point of inflection, we went from concave upwards to concave downwards. So not only is this a point of inflection, but it is also a point of diminishing return. So we are ready to answer the question. We are concave upwards from -infinity to -2 and 4 to infinity. Concave downwards from -2 to 4. I have a point of inflection at -2, comma the original function evaluated at -2, which turns out to be -35. And I have a point of inflection at 4, comma the original function evaluated at 4, which turns out to be -45. And as we said before, since at this point of inflection we went from concave up to concave down, it is also a point of diminishing return. Let's take a look at another one. Let's determine the concavity of x to the 4th over 12 minus x cubed over 3 plus x squared over 2 plus x minus 5, and identify any points of inflection. Same thing, this 12, 3, and 2 are all coefficients. You can just leave them. So the first derivative will be 4x cubed over 12 minus 3x squared over 3 plus 2x over 2 plus 1, which will reduce to x cubed over 3 minus x squared plus x plus 1. Now I can take my second derivative. I get 3x squared over 3 minus 2x plus 1, which will reduce to x squared minus 2x plus 1. I'll set that second derivative equal to 0, factor, and set the factors equal to 0 to realize I have one point, critical point of the second derivative, and that's going to be 1. So in dark blue here, I labeled my interval, or I labeled my number line with just this one critical value. So my intervals are going to be -infinity to 1 and 1 to infinity. I'll choose an x value from the first interval. I'll choose an x value from the second interval. and I'll plug those x values into the second derivative. Notice when I plug in 0, I get 1, which is positive. And when I plug in 2, I get 1, which is still positive. So my function is concave upwards, and then it's concave upwards again. So it turns out that this function is concave upwards from negative infinity to 1, and it's concave upwards again from 1 to infinity. So it doesn't actually change concavity. It's never concave downwards. So it's concave upwards from negative infinity to 1 and 1 to infinity. It is not concave downwards, and because it doesn't switch concavity, it did not go from concave up to concave down or concave down to concave up, there are no points of inflection. Let's do one more example. We'll determine where this function x cubed minus 9x squared plus 24x minus 18 is increasing, decreasing, concave up, concave down, and we'll identify any relative extrema and points of inflection. So we're mixing previous knowledge with today's knowledge. So remember, when you do your increasing, decreasing, and relative extrema, you're going to use the first derivative. So we'll find the first derivative, 3x squared minus 18x plus 24. Set the first derivative equal to 0, factor out the 3, and then factor the remaining trinomial to get two critical values, 2 and 4. So I drew my number line labeling 2 and 4. I have my interval negative infinity to 2, 2 to 4, and 4 to infinity, and I chose an x value from each of those to plug into the first derivative. Plug in 0, I get 24, which is positive, so I'm increasing. Plug in 3, I get a positive times a negative times a positive, which gives me a negative, so I'm decreasing. Plug in 5, I get a positive times a positive times a positive, which is a positive, so I'm increasing again. So using the first derivative, I can see that my original function is increasing from negative infinity to 2 and from 4 to infinity. It's decreasing from 2 to 4. I go from increasing to decreasing at 2, so that's going to give me a relative maximum at 2, the original function evaluated at 2, which turns out to be 2. And at 4, I went from decreasing to increasing, so I'm going to have a relative minimum at the ordered pair 4, the original function evaluated at 4, which turns out to be negative 2. So all of this in light blue here, I used the first derivative to determine increasing, decreasing, and relative extrema. Now I'll take the second derivative of this in dark blue here to get 6x minus 18, and I'll use the second derivative to determine my concavity and points of inflection. Set my second derivative equal to 0, and I get 3. I labeled my number line here with 3, and my intervals are negative infinity to 3 and 3 to infinity. I chose an x out of here and an x out of here. When I plug 0 into the second derivative, I get negative 18, which is negative. That means I'm concave downwards. When I plug 5 in, I get 12, which is positive, which means on that interval I'm concave upwards. So now I can answer the question. I'm concave upwards from 3 to infinity. I'm concave downwards from negative infinity to 3. I did switch concavity right here at 3. I went from concave down to concave up. So at 3, the original function evaluated at 3, which turns out to be 0, is a point of inflection. But it is not also a point of diminishing return, because we went from concave downwards to concave upwards. So there's our lesson on concavity and points of inflection, and I'll see you next time.